Let's look at a famous failure. In the late 1800s, an experiment set out to confirm a core property of the universe found nothing at all, leaving the scientific community without its most important foundation. By this time, physicists were certain that light behaved as a wave. In the natural world, every wave needs a medium to travel through. Ocean waves move through water, and sound waves move through air. Logic dictated that light must have a medium of its own. They called this substance the luminiferous ether. It was imagined as an invisible, frictionless material that filled every corner of the vacuum, providing the physical structure necessary for light to travel across space. The physicist Augustin Jean Fresnel proposed that this ether was completely stationary. If that were true, as the Earth orbits the Sun at 30 kilometers per second, it should be plowing through this cosmic ocean, creating a constant ether wind rushing past us. This wasn't a fringe idea. The ether was the starting point for every calculation in optics. Scientists just needed a way to physically measure this drift to prove their model was correct. James Clerk Maxwell, perhaps the era's greatest theorist, spent years trying to calculate how the Earth's motion relative to this stationary ether could be detected. This visualization shows the scale of the problem. The large block is the speed of light. That microscopic sliver at the bottom is the Earth's orbital speed. Maxwell realized the effect of the ether wind on a beam of light was proportional to the square of that ratio, a difference of roughly 1 part in 100 million. Maxwell eventually concluded that the effect was too small for any laboratory instrument to detect. He even went as far as publishing his belief that an earthly measurement of this second-order effect was strictly impossible. But Albert A. Michelson, a young U.S. Navy officer who had spent years refining measurements of the speed of light, didn't accept that conclusion. He saw Maxwell's impossible calculation as an engineering challenge. Michelson set out to build a highly precise new machine that could measure a value Maxwell insisted was completely unreachable. In 1881, Michelson developed a new kind of instrument, the interferometer. Its sole purpose was to trap and measure that elusive ether wind. The device splits a single beam of light into 2 paths. One beam travels in the same direction as the presumed ether wind, while the other travels perpendicular to it. The core logic is based on travel time. Think of a swimmer going upstream against a current and back versus a swimmer crossing the same river sideways. The light beam fighting the ether headwind should take slightly longer to complete its round trip. When those beams reunite at the observer point, that tiny time difference should cause their waves to be slightly out of step. This would create a visible shift in the light's interference pattern, a smoking gun for the ether's existence. Michelson ran his first test in Berlin, but the experiment was plagued by trouble. He made a mathematical error in his predictions, and vibrations from city traffic outside shook the delicate brass arms of the machine. The 1881 test failed to produce a clear result, but it proved the interferometer could work. Michelson realized he just needed a machine of much higher stability. Years later, Michelson teamed up with chemist Edward Morley in Cleveland. Together, they designed a much larger, ultra-sensitive version of the experiment. To stop vibrations, they mounted the entire optical system on a massive sandstone slab and floated it in a trough of liquid mercury. This allowed the entire machine to rotate smoothly without any friction from the ground. They also increased the sensitivity by using extra mirrors to bounce the light back and forth. This effectively made the arms 10 times longer, multiplying the expected time delay by 10. Their math was precise. Rotating this floating stone should have produced a clear, undeniable shift in the light's pattern of about 0.4 fringes. They rotated the slab and checked the eyepiece. There was no shift. The pattern remained almost perfectly still, with at most a tiny flicker of 0.01, well below what the ether theory required. They had built the most accurate measurement tool of their time, only to discover that the medium they were looking for wasn't there. The results were a shock. Michelson and Morley hadn't just failed to find the wind, they had provided empirical evidence that the stationary ether theory was likely wrong. Some physicists were so committed to the ether that they tried to create a desperate mathematical patch for the theory. Among them were Hendrik Lorentz and George Fitzgerald. They proposed a radical idea: What if the instrument itself was changing shape as it moved? This is called length contraction. They argued that any object moving through the ether physically compresses in the direction of motion. They calculated that this shrinkage happens at the exact rate needed to cancel out the time delay, making the ether drift impossible to measure. It was a bizarre suggestion that the physical dimensions of an object depend on how fast it's moving, but at the time it was the only way to keep the old model alive. Eventually, the mounting evidence forced physics to move on. Scientists realized that if the ether couldn't be detected, it probably didn't exist, and the speed of light must be the same for everyone. This insight, that the speed of light is the only absolute, and that space and time must bend to keep it that way, formed the basis of Albert Einstein's theory of relativity.